Okay, so we have come quite far into this course now. We started off by learning about kinematics, after which we had uh, taken up forces and force systems and axioms. Then we followed it up by dynamics. And finally, we are now going to learn about statics, which is, as you will see, somewhat of a special case of dynamics. And most of us who are learning statics will find it much easier because the sort of more rigorous part or more involved part of this course is already over. So let's begin with that. We begin learning about statics by some remarks on the equations of equilibrium. Okay, just to see what will be useful for us in this case. Okay, now so let's just call this as remarks. Okay, so remarks on the equations of equilibrium. So if we have a system which is in equilibrium, okay, so the external loads on any part the external load on any part part P, okay, this must satisfy okay, so f of P is equal to 0 and ma for this part must be equal to 0. Okay, now the second one is that if these equations 4.1 are true for all the parts of the system, okay, then they will be also true for the whole system. So if f of P is equal to 0, sorry, 0 again as a vector, ma P 0 for all parts P of a system B, okay, then f for this entire body is equal to 0 and this ma for this entire system is equal to 0. And the converse of it is not true. Okay, that means, I mean, if the whole body is in equilibrium, that doesn't mean that individual parts of it are also in equilibrium. Okay, so the converse is not true. So an example of it can be, say, a disk B of mass m rotating at constant angular velocity about a fixed axis. So f of B is equal to 0, ma of P is equal to 0, but if you take for its semicircular part, its center of mass C, it will have these forces half mac, which will not be equal to 0. Okay, so that's why we say that The converse of this statement is not true. Okay, now moving on. For a rigid body B, if for the whole body f of t is equal to 0, ma of t is equal to 0, then it remains at equilibrium. It remains in equilibrium if it is initially in equilibrium. Okay, so if at time equal to 0 it was in equilibrium, then it will continue to be in equilibrium. Okay, this was for a rigid body. So let me put the next one in green. For a deformable body initially in equilibrium, if you have, say, this ma for all parts B are not sufficient to ensure equilibrium. Okay, so most of our focus is on rigid bodies, but this is just one statement about deformable bodies, okay, which we are not really studying in this particular course. And then there are some other conditions related to it which I don't think you need to learn at this stage. Okay. Now, if you look at this equation 4.1, one of the claims which is made by the authors in your text is that it is difficult to verify equations 4.1 for infinite number of parts of a deformable body. Okay. So the way it is written is that we sort of write a set of partial differential equations in terms of stresses. That is again something you don't have to learn at this stage, but those equilibrium equations, those partial differential equations, if they are satisfied, then what they mean is that 4.1 is satisfied. Okay. So let me put down that also. These are some things which you will perhaps learn, the ones among you who go into, say, to learn solid or fluid mechanics in your second years. Okay, right now you don't have to know this. So the idea is that equations 4.1 cannot be verified for infinite number of parts of a deformable body. So what happens is that you have so-called equilibrium equations which occur as partial differential equation, and these you can check, say if you have a deformable body, so you can check at any given point on this that partial differential equation is satisfied or not. Okay, so that is what the idea is, and if this is satisfied at this given point, then it means that this equation 4.1 is satisfied. So we are not learning about those partial differential equations at this stage. Okay, so these were a few comments about this. Let's now move ahead and learn something which will be very useful in our understanding of statics. So if you have, say, a body like this, and you have F1, you have F2, okay, so we can show that for a system in equilibrium under three concurrent forces, the forces concurrent because they are all acting at the same point. The forces F1, F2, F3 can be represented as the sides of a triangle, can be represented by sides of a triangle, okay, taken in order. So let me draw F1, okay, F2, okay, and F3. So between F1 and F2 the angle is what? Alpha 3. Between F2 and F3 the angle is what? Alpha 1. And between F3 and F1 the angle is alpha 2. So this is how you can represent the forces, and the length of these sides clearly are the magnitude of these vectors F1, F2 and F3. And so you have Lumi theorem that would tell us that you have F1 by sine alpha 1 equal to F2 by sine alpha 2 F3 by sine alpha 3. So this is called equation 4.2, and this you should verify. I mean, you should have done this at some stage in your life, but verify that this follows sign formulas. Yes, I think you have enough hint to do this. Please verify this for this situation. Okay. Now there are some observations which one can make. Well, it puts that the following observations observations about a system in equilibrium may be made. About a system in equilibrium may be made. So if you have, say, a part P of a system, so when I say system, it can be like a system of many rigid bodies, or it can be a part of a body. Okay, sorry, when I say a system, it can be a system consisting of many bodies, or it can be one big body. Okay, so a part of it will be part of this body, or a part P of a system can also be, say, one complete body in itself. Depends on how you define your system. So for its part P, F is equal to 0, MA is equal to 0. This gives 6 equations. Let's write them down. This will give you 3 equations because it's a vector. So fx will be 0, fy will be 0, fz is 0. Similarly, this is also a vector equation, so it will give you 3 equations. So max will be 0, may is equal to 0, ma z is equal to 0. Okay, so let's first draw our diagram and see what this is. So this is a body and this is the direction E, force F1, force F2, okay, and at this point A, and this is B, so you have this RAB, you have this MA, this is F acting, and then say you have this C1 acting. Okay, now given this force system, let's make this observation, which is that we do not get any more equations independent of F is equal to 0 and MA is equal to 0 by writing say MB is equal to 0. Okay, so just because you choose a different point to write the moment about, it doesn't give you independent equations. Okay, now the reason for this is, if you use the equivalent force couple system F and MA at A, then MB would actually be equal to MA plus RAB cross F is equal to 0 is automatically satisfied. How do we know? Because this is 0 and this is 0, F. Okay, so that's why this equation will always be satisfied. So it doesn't really give you an independent. Yes, it will look like a new equation, but it's not independent. Okay, so that's just something which you should keep in mind, and that's why you just choose one important or one sort of clever point to write this MA is equal to 0 about. Okay, in statics, that's it. You don't have to keep on hopping from one point to another because they won't really give you independent equations. It may be needed in some cases if you are, say, taking two separate bodies, okay, or parts separately, then of course you have to do that, but for one given part you do not have to write this because it will not really give you an independent equation. Okay, we do not get an independent equation by taking the component of f. We do not get any book. We're taking of along another direction E. Okay, so for example, FE will be equal to F dot E. You can see this direction E over here, so I should put it like in a hat. Okay, so this will automatically, since this is automatically satisfied. Okay, why? Because I mean this, if f is equal to 0, then there's no point in taking its projection along any direction. Okay, fine, so this is there. Now if you take up 4, okay, for a system of n interconnected of n interconnected rigid bodies, we can write 6n scalar equations of equilibrium. I mean, the reason is that you can write, say, for six equations for each body, and for n bodies it would be 6n equations. Now the important part is that the equilibrium equations of the total system, of the whole system, is not independent. So how would we write? We would say that this is not independent of these equations. Of these 6n equations. So I mean the whole point is that the internal forces will cancel if you take the whole system, but these are not like independent equations. Okay, so that's again something which you can note. So finally, let's list out the independent equations, okay, for various systems. So let's do that. Independent equilibrium equations for various force systems are, so let's see, in a general case, one, two, three, or x, y, z, you have 6 equilibrium equations. Fi is equal to 0 and say MOI is equal to 0. Then let me call it ABCD. AB. Then say if you have a concurrent Okay, spatial meaning in a 3D. Current spatial. This would have only three equilibrium equations, which would be what? Fx equal to Fy equal to Fz equal to 0. Okay, so all the three individual components would be equal to 0. You can write, say, parallel to z-axis, again spatial. This would also have three. One is that Fz is equal to 0, then the moment in the plane, they will all be equal to 0. Okay. Now if you look at coplanar with forces in xy plane, okay, and then this would be fx, fy, moz will be equal to 0, and similarly coplanar with forces parallel to x-axis in xy plane, then you should be able to have only two equations, fx and moz is equal to 0, and coplanar and concurrent in xy plane, this has only fx and fy is equal to 0, and then you have, say, all forces intersect in a line, so x-axis for example, then you will have five equations, fx, fy, fz, moy, moz equal to 0. Mox will not be. Okay. Now let's take up this topic of statically determinate and statically indeterminate system. This is extremely important, and it goes all the way to your final year of your education and even beyond that. So you shouldn't have any doubt about when someone asks you what is a statically determinate or a statically indeterminate system. We have actually somewhat referred to it earlier also, but let's do it in a slightly more grander way this time. So statically determinate. I hope you recall where we have discussed this statically indeterminate situation. Yeah, I think in the previous discussion on dynamics. System. Okay. So how do we solve say solving an equilibrium problem? So I'm writing general because generally we can solve it like this. Okay, so what all do we need? Let me put it first using equilibrium equations. Okay, and boundary condition on forces. Then you can have, say, deformation equations. Okay, geometric fit, compatibility. And this word is not very hard to understand. So for example, if you have this say inner, so this is a plate and this is contained in an outer fixed plate, outer hollow plate. Okay, so yes, I mean, say if you give it heat and then it will try to expand, but the maximum it can expand is, say if this is a outer rigid plate is rigid or it is fixed. Okay, so the maximum this inner plate can expand is until this boundary, right? So this is some sort of a geometric fit or compatibility. It cannot go beyond that. So that's the meaning of deformation equations. And lastly, you have the force deformation relations. So the relation of how this forces and deformation are related, that's the third part. So generally all these three things are sufficient. Now there are special cases, okay, and I'm putting that in another ink. In some systems, so all unknowns reactions, okay, and internal force can be found only using one, which is the equations of equilibrium, okay, without taking into account any deformation. Deformation. So this is called statically determinate. So clearly, if you do not require the relation between force and deformation, see, for example, for a linear spring, this is, say, the relation between force and deformation, okay? Now, K is a spring constant which depends on the material of the spring and so on. So if you don't really require this force deformation relation, for a statically determinate system, we can find out all the unknowns without, I mean, independent of the material properties of the body or parts of it. Okay, so that's how we can go about it, because this is a material dependent on the material. Okay, and lastly, and that's where the distinction comes, if all three 1 2 3 governing equations, this is just a fancy word for these equations, governing equations, okay, if all the three governing equations have to be solved together, this together word is important, okay, because they are of course related to each other. I mean, the force and the displacement are related to each other, so they have to be solved together. Okay, now for finding all the forces involved in a system, okay, then you call it statically indeterminate. Okay, so the idea is if you can just solve it by a force and moment balance only, then it's called statically determinate. Otherwise, it's called a statically indeterminate system. Okay, and it is the whole system which is called a statically determinate or statically indeterminate system. Okay, this is something which you should keep in mind. And over here clearly I have given you the example of a spring, so it will depend on the material properties also, the indeterminate case. Now, even within this statically indeterminate, there are certain sort of varieties or variations. A system is said to be statically indeterminate externally or externally redundant if the support reactions cannot be found from equilibrium equations alone. So this is a case if which say you have a joint or a hinge or some sort of a support, okay, and if you cannot find those sort of reactions at those constraints and supports just by the use of equilibrium equations, then we call it a statically indeterminate externally or externally redundant. Okay, now obviously there has to be a system which is called is said to be statically indeterminate internally if the internal forces resultants cannot be found using only the equilibrium equations. When I say equilibrium equations, I think we have emphasized enough that it is both F equal to 0 and MA is equal to 0, both of them. Okay, so a system is said to be statically indeterminate internally if the internal force resultants cannot be found only using the equilibrium equations. And then a system is these are all variations of indeterminate. System is said to be certainly indeterminate indeterminate if the number of unknowns unknown forces, and moments exceeds the number of independent equations of equilibrium. And we have gone through several situations of how many equilibrium equations exist over here. Okay, I think this was G. Okay, so these are all, I mean, for example, in this case, if the number of unknowns is more than 3, then you would call it a certainly indeterminate. Okay. Okay, so this is a sufficient condition for static indeterminacy. So if you have a situation where the number of unknowns are more than the numbers of equations of equilibrium, independent equations of equilibrium, then you don't have to like start solving and then come to the stage and say, well, it seems now we cannot solve it only using equations. You can just count the number of unknowns and compare, and then you would know. So because it's a sufficient condition, so you would then exactly know that you have to use the deformation equations and the force deformation relations. Again, it may not be a necessary condition. So this is something which you can think of. Why? Okay, you can think of a situation in which one case it is sufficient, but in the other case it's not necessary, and argue to yourself why this is sufficient but not necessarily necessary, but not definitely necessary. So clearly, I mean, if you have, say, I mean, just look at this particular. So if you have a rigid body, okay, and if the number of unknown reactions is more than 6, then clearly you are statically, the system is statically indeterminate. Okay, and if you have, say, coplanar force system in an xy plane or any plane, and the number of unknowns is more than 3, then again it is statically indeterminate. Okay, so this list is somewhat exhaustive, so you don't have to worry about finding a very new case later, but if you have to, you should be able to do it with all the knowledge which you have. Okay, so let's now start using some variables for this, and this somewhat merges with your linear algebra, understanding of linear algebra, where you write the equations, system of linear equations as matrices. Okay, if the number of equations of equilibrium m is more than the number of unknowns n, then these equations are linear in the unknowns, and these equations are linear in unknowns. So you know what a linear equation is by this stage. Then you can write it in the matrix form. Matrix form. AU is equal to B. So A over here becomes what? M into N matrix. U, the unknowns, will be N into 1, okay, column matrix. Okay, and B is a M into 1 column matrix. Okay, so once you have a system of linear equation, there are certain methods like Gauss elimination method and so on, which you can use to solve. So there is also this smaller system, say 2 by 2 system, you can just solve it like that. For 3 by 3 system also you have these little formulas, but normally in a mechanics problem you would have lots of unknowns, so it's better to go with a augmented matrix or some Gauss elimination method, where you take a pivot point and then you try to create a diagonal matrix. So those sort of things have to be done, but the construction of that is what you have to be confident about in this course. I mean, to solve it, perhaps you will learn it in other courses, and definitely you will learn it in other courses, but you should be able to construct that system AU equal to B using the knowledge over here. Okay, so this is also something I'm putting in red because it's coming in from your understanding of linear algebra. A unique solution exists if the rank of matrix, I hope you know what is a rank of a matrix. If not, you should just stop and learn about and then come back. It's only a matter of revision, I think. And that of the M into N plus 1 augmented matrix is each equal to N. Okay, and then in this case it is a statically determinate. Okay, so this is coming from your linear algebra, and you should be aware of it one way or the other by the end of your first year. Okay, if M is equal to N, then there is a unique solution provided the rank is what? The rank of A is N. A is non-singular. So the rank is what represents the independent columns which you have, okay, in any matrix. So you can take certain examples, for example 1 2 3 4, and say 1 3 2, 6. Okay, so what should be the rank of this, what should be the rank of this, and so on. I think you should have these ideas by now. Okay, so let me take up one example over here. I'll just take up one. So you have this cantilever, this C, this is P, this is T, this is Q, linearly varying, then you have this P, and then you have A. This is fixed into the wall. Okay, now if I separately draw this, because of the, first of all let me draw what is already given. C is given, this P is given, and Q is given. Now at A, the constraint is that it will not be moving either in the x or y direction. It's a planar problem, nor will it allow a rotation. So for not moving in the y direction, I have to have R1. Not moving in the x direction, I have to have R2. And not allowing a rotation or a free rotation is C1. Okay, so this is how we write this. Okay, and now we can take up one part of it, which is dB. So D is somewhere over here, dB. Okay, so you have C, and then P comes up like this, and over here you have this internal forces, shear, normal, and moment. Okay, so this is an example of a statically determinate system. Okay, so what are the reactions? So R1, R2, and C1. Okay, okay. So you should know the unknowns. So for a coplanar, let's see, you have three unknowns, okay, and you have three equations. So that's why it's a statically indeterminate. Provided this condition is satisfied, okay. And anyways, the rank counts the independent, because you see this is the independent equilibrium equations. So the fact that rank is already considers as independent. So just don't count it. It should also be independent. Okay. So there are more cases where one can see this. I think this can only come up by solving lots of problems. Okay. So I hope you will be able to do that. So then there are some discussions about a deformable body, which perhaps we may not need to do at this stage. One of the points which I am writing in green, okay, here, which you don't really need to follow up, that's that the amount of deformation of a body does not necessarily indicate whether it should be modeled as a rigid body. You can take it just as a proof. I mean, the idea is that you compare it and then you can see that, so you don't have to do it over here. So what we do is we will be focusing only on statically determinate only. Okay, the more complicated one, which is a statically indeterminate one, which will be done by a few of you who go on to study courses in, say, mechanical or civil or materials or mechanics, textiles and so on, or chemical engineering perhaps. Okay, so this is what we'll be confining, but you should know exactly what is statically indeterminate, all of you. There cannot be an exception for that. Okay, so there are several examples of one rigid body, okay, which perhaps you should look up from your textbook. Several of them are given, and it will take more time for us to understand those examples, and it will be simple enough, but it should be done nevertheless. Okay. Okay, so we'll be learning now about the frames and mechanisms. Most of the discussion which happens now will more be about how to solve the problem rather than the actual problems, and then the solved examples are given in the text for you to learn them yourselves. Okay, so let me first define a system consisting interconnected rigid bodies is called a frame if the relative configuration of the bodies cannot change, else it is called a mechanism. This means that it is under constraint with at least one possible change of relative configuration. Okay, so let me just show So this is a frame. The relative configuration of the bodies in this do not change. Okay. On the other hand, if I show you something like this, so you have this body 3, body 2, body 1, mx like this, omega is like this. This is a mechanism. Okay, so I've just taken two simple examples to bring home the point, the difference between a frame and a mechanism. Okay, so most of the machines around us are actually mechanisms because they have moving parts relative to each other. Okay, so a mechanism, machine is a mechanical device which transmits and modifies applied forces, moments. So when you know the examples of it, and you should convince yourself that you exactly understand how this is done in a lever, okay, an inclined plane wedge, pulley, okay, screw, okay, or a nut, whatever way you would call it. Okay, so 1 2 3 4, and then there should be one more, which is say wheel and axle. So please check up some sort of an internet video, etc., to ensure that each of the 5 names which I have written over here are mechanisms, and what they do is they transmit and modify the applied force or moment. So make sure that you exactly understand this part of modifying the applied forces and moments in all of them. Okay, so these 5, these ones are called simple machines. Okay, so the idea is that if you give an input load, a load may be either a force or a moment, these machines will help you get an output which is having a magnitude which is different, or the direction and the direction either ways different from the input one. Okay, so that's how they help in modifying the applied forces. So all of these 5 you should be able to learn. Okay, simple machines. Okay, now the mechanisms in general or machines, there is change in configuration because that's how we define it, right? I mean, the relative change in configuration is there of the parts, and not all of them will be in equilibrium all the time. Okay, so some of them may be, say, translating or accelerating angularly or in any other way, so they will not be in equilibrium. under given loads. Not all of it will be in equilibrium, maybe there are some parts in equilibrium. Okay, so because there is a change in the configuration, the unknowns in mechanisms will be some unknown forces, unknown forces, moments, or I could have just written load, and some unknown coordinates specifying its equilibrium condition. Okay, so the coordinates have to be there, and the coordinates are usually the ones which are specifying an equilibrium configuration. Okay, now for the frames, the story is much simple. This is just forces or moments. Okay, because there is no relative change in the configuration, so it's not occurring as an unknown over here. Okay. Okay. Now a frame or mechanism may include members that are not two force members. Okay. So that would mean that it has some sort of a bending moment or a shear or an axial forces and so on. Okay. So there may be members either in a frame or mechanism which may not be two force. So that will automatically slightly complicate, and if there are two force members, you should identify them first and sort of write those relations immediately, because they help in solving the problems much more easier. Okay, so how you approach a situation, I mean, to solve, say, a problem or a physical situation of frames and mechanisms depends on a case to case basis. So there is no general method how to go about it. Okay, and I mean, you have to, for example, out of the whole given system, you have to choose subsystems and write the respective equilibrium equations for that. Okay, after the free body diagram and so on, and then you keep on proceeding. So this selection of what I should choose as the system comes by experience, and it would come to all of you as well as you learn about the subject and see more solved examples and try to solve more questions on this subject. So one of the sort of situations you may meet if the frame is a rigid unit by itself, when removed from its external supports, and the supports provide 6 equilibrium equations. Okay, 3 for forces, 3 for moments. Again, if it's a 2D case, then it would just be 3, right? 2 for force, 1 for moment. So it's 6 constraints, independent constraints, And you also have the same number of six equilibrium equations. Okay, so there is no problem as such. So if the frame is rigid unit by itself, okay, you have to mark out these words, then you have a situation like this. On the other hand, if I mean, it may consist of rigid parts, but the system which you have selected, if it is not rigid by itself, okay, uh, without the external supports, if it is not rigid, then the constraint reactions are clearly greater than 6, okay, for a 3D case, and then using that you can make it a rigid frame. So you apply extra constraints to make it rigid, and hence you can sort of then proceed to solve. So for the whole structure, clearly you will be short of such equations because you have artificially added some things. So the support reactions for this case cannot be determined from the equilibrium equations of the whole structure. In such a case, it is usually necessary to first consider the equilibrium of some portion of the system that itself is inherently rigid. Okay, so this is so you proceed in this way: identify the rigid ones before rigid subsystems first. Okay, and then you proceed for the later parts. Again, as I have said before, identify the two force members first. That's the easiest thing to do, and it should be possible for you to do that since you have learnt about two force members. Now, one of the doubts which you may have, and perhaps I mean it becomes more clear when you look at solved examples. Say example, you have something like this, and then you have, so this is a pin joint, okay, and now you want to clearly separately draw the FBD, okay, or you show the pin in this one, or in the other case you show the pin in this one, okay. So the pin is there, and you have to now, I mean, once you show the FBDs, the question is that in which member should I show the pin, okay. Now the answer is that it does not matter where you assume your pin to be, okay. So that at least in this situation it does not really matter, so you can just solve it in either way, and it will not give a problem. The cases where it can make some difference is when you have, say, more than two members which are connected by a pin, say something like this, okay. This is three members, so this will be this can make some difference, okay. Now two members are pinned to a support, that's the other situation, and an applied load acts on a pin connecting two members. So if the pin itself says like this, and then there is a force on the pin, okay, in this case there is no force on pin. So if situations like this happen, so then you have to really be careful in how to, or in which member to show the pin, okay. So that comes again by experience of how there is no sort of rule to share at this moment. But this is something, when you come to this situation, this is something which you should be noticing when you read the solved examples and see how that thought process builds up, okay. So let's take up some examples. Have So let's say this is P1, this is P2, this is P3, 4D, P. Okay, say, sorry, then, okay, two, this is F2. Now let me draw this 3. So this is pin B, and you have what, F1, F2, this pin, okay, at P, and this is pin A, pin A, R4, R1, sorry, R3, right? Yes, so it would be R3, and then this is A again, no problem. Now let's look at this member 4 also. This is pin D, this is pin C, P1, F1, this is 3, this is 4, this is P2, then R2, F2. Okay, now first of all, please look up at this system of what, 4 members, right? 1, 2, 3, 4. So this is system of 4 members. So 1 and 2 are identified as 2 force members, okay, which has been shown accordingly. So don't consider pin as a part of this because it is 2 force members, so just let it be like that, okay. So don't consider pin over here because you see all the pins over here, uh, either at B or at D, these are having more than 2 members, or over here it is supported, okay. So it falls in that category of 3 exceptions which we had identified, okay. So the pin will make a difference if more than 2 members are connected by a pin, or 2 members are pinned to a support, or an applied load acts on a pin connecting 2 members, okay. Sorry, in this case there are not 3 members, but then there is an applied load over here, okay. So because you have identified these 2 force members, don't consider pins as a part of this, okay. Now if you don't consider them a part of this, then it becomes quite simple where to take the pins. So pin CD should form part of member 4, this one, okay, and pins AB should be a part of member 3, okay. So once you do this, draw the free body diagram, okay, and then you can solve this, I mean apply the equilibrium equations. So what are the unknowns? So this is F1, F2, R1, R2, R3, R4, So there are 6 equations of equilibrium, okay, for the members 3 and 4. So we can say that, say, MC is equal to 0 for member 4. Okay, this should yield F1. Okay, so for member 4, if you balance the sort of moments about the spin, so a lot of these R2, F2 and R1 will be there. P1 is a known force, so F1 you can get, because that P1 and P2 are known, so F1 you will get out of this. Okay, now you say MA is equal to 0 for member 3. Okay, so clearly this R3 and R4 would disappear. F1 is already found out, so then you can find out F2. It's F2 because F1 you would have just found over here. Okay, now F is equal to 0 for member 4. Let's see if for member 4 over here. Yes, so F1 and F2 have been found out. Okay, and if you apply the force equilibrium in the x direction and in the y direction, then we would get R1 and R2. Similarly, F equal to 0 for member 3, this yields what? R3 and R4. Okay, because F1 and F2 has been found out, R3 and R4 are the only unknowns. Okay, so that is how we can approach the frames and mechanisms, and there are several solved examples in the text which you should be looking at. Okay, so when you notice it, please look at the thought process behind this. You may not agree to it at that moment, but you should at least be able to appreciate the thought process behind choosing, say, a system, or in what system I am taking the frame, pin joint and so on. Okay, so that's what we can learn, and when you actually solve your problems, then you can do it either way, and that also gives an experience. Okay, so the next topic again which we are briefly discussing is about friction. Okay, so problems involving friction. So there are two types of this. One is to find the condition of conditions for impending motion. Okay, or uniform translation. And the second category is to find out whether a system remains in equilibrium under given applied loads. Okay, so every time you see a problem of statics involving friction, you should try to identify them as either of them. Okay, so there may be a combination of the two as well, but it should be very clear of which category we are looking for. Okay, now the way to solve, one way, I mean, we never claim that the way to solve, we just claim one way. So this type of problem, type 2, one way is to find the applied loads required for impending motion in various possible modes, and then compare with actual applied loads. I mean, this is one way, or the other way is you find the value of the parameters, say friction coefficient mu, or the position of a load, okay, for impending motion, and then compare it with the given value to see whether it is actually a case of impending motion or not. Okay, and again, I mean, just to check whether there is a no slip. This can be checked. So normally this is of this situation. Okay, or F. So this is how easily one can check for impending motion is there, and the second case is uh, if it is remaining in equilibrium, then all of the values should match essentially. Okay, so both ways you can do. Again, there are several solved examples which use these ideas in your text, which you should be considering. Let's take up some special cases, which is say impending motion with tipping or slipping. Now the check which you want to do, I mean, many a times what happens is that when you are trying to make a body slip, uh, it can also tip. Okay, so we want to check whether a body which was actually in equilibrium and is subjected to say a gradually increased load, it loses its equilibrium by impending slipping or impending tipping. Okay, we have to check that part. So the way to do this check, what are we trying to check? Let me put that in green. Check if a body initially in equilibrium and subjected to a gradually increasing load loses its equilibrium by impending slipping or impending tipping. So let's take up a example. So you have this P acts like this. This is assuming the center of mass. So mg acts over here. X is this distance. Just make it. X is the point where this n acts, and then you have this mu s n. Okay. And then we can take up, say, a second example. Where you have this P. Okay, this is a very practical situation. Say you are trying to push an Almira or something. Okay, so you want it to slide, but then there's always this risk of tipping. So that's exact situation which we are trying to study over here. Trying to move an Almira, a fridge, or a washing machine. Okay, fine. So now the way to sort of go for this is to assume impending slip and find the line of action of n or n1 n2. So in this case you are trying to assume impending slip and then find at what position x the force n acts, okay, or what is the value of n1 and n2. So these are two separate problems. Okay, this is, say, A and B. Okay, now if x, which is the so-called line of action of n, okay, is within the convex envelope. Let me put that in red so that you can visualize this. If x is within the convex envelope of the area of contact, then impending slip is physically realizable. Okay, so this check you have to make, that if x is within the convex envelope of the area of contact, okay, then the impending slip is physically realizable. So you have to try to understand what is this convex envelope of the area of contact. Okay, it's not the actual area of contact but the convex envelope of the area of contact. You will exactly understand this once you try to draw, or once you try to visualize how this impending slip will happen. Okay, now in the second case, which is B, if n1 n2 are greater than 0, okay, so if this is for A, this is for B, then impending slip is physically valid. Okay. Now if these conditions are not met, for example, if you have not met, if x turns out to be negative, okay, or n2 turns out to be negative, then there is tipping. Okay, so this is the strategy which you must follow to decide what is happening, sliding or tipping. So for A, the tipping would look like this. This, I mean, the FBD must be, so you have P, you have MG, and you have this point A. This is how tipping would happen at the end. And for B, if tipping is happening because this condition say was not met, n2 is smaller than 0 or n1 is smaller than 0, whatever, then in this case just so for n2 smaller than 0 you will have say P, mg, and you have f, and you have n1. Okay, so this is how one can find. Okay, so f in these cases will always be less than a limiting value. I mean, the reason is, I mean, if it was at the limiting value, then the slipping would be happening. So you don't do that. Okay. So again, there is an example for this particular case which you must check from your textbook and understand it well enough. Okay. Now let's take up impending rolling of a cylinder with contact at two or more surfaces. Okay. So impending rolling of a cylinder with contact at two or more surfaces. Think of it like this. Okay, sorry, not this. Think of it like this. Okay, so this is like a step. Okay, so at two or more surfaces, so this is contact over here, and this is contact over here. One can also have another situation, say you have something like this. So then this becomes the third point of contact. So this is what we are trying to sort of understand when you have an impending rolling of a cylinder with contact at two or more surfaces. Now, what is the doubt? The doubt in such cases is at what contact point slipping is happening and at what other contact point slipping is not happening. Okay, so say you have two contact points. Okay, I'm just like removing this third one just for the sake of simplicity. I mean, it can have as many as you want, but the strategy remains the same. So consider a cylinder with two contact surfaces with possibility of slip at one and no slip at the other. Now notice the words very carefully. Consider cylinder with two contact surfaces with possibility. Okay. Now what I want is, I mean, I have just drawn this diagram to show you this, but I am removing it now so that you don't confuse this with this particular case. Okay. So I'll just remove that. So there's a possibility of slip at one end and no slip at the other end. Okay. Now how do I proceed? Just like in the previous case, you assume impending slip at contact 1. Okay, say, so if there is a impending slip at contact 1, then you have the, say, reaction force N1 and F1 is equal to mu S1 N1. So this condition must be there again, and this friction will act in the direction which is opposite to the impending slip. So I'm not mentioning all that. And then a no slip happens at 2, no slip at contact 2. So in this case the reaction is, say, N2 and F2, and we don't have a value of F2 over here because there's no slip happening. Okay, now solve the equations of equilibrium. And check whether the assumption of no slip holds. Okay, so I mean, what would be the check of no slip? That F2 will be smaller than equal to mu S2 N2. This is the condition for no slip. If this is true, then it means that what you had assumed is correct. Okay, and if it is not satisfied, then you reverse this. For example, then no slip, then you rework the problem again with no slip at contact 1 and impending slip at contact 2. Okay, and then do that check. So this time it should satisfy because there are only two possibilities. Now clearly for two contacts it was easy to do, and I mean, you know how to proceed. If one is not true, then the other will very likely will be, though you have to rework and check. Okay, you cannot directly claim that. Okay, and that is where the difference comes in trying to solve a problem. Okay, so if you have to, say, take a guess, and two students, say, one of them assumes this contact 1 is impending slip and the other assumes contact 2 is impending, and they would clearly spend different amounts of time to get to the correct answer. But this is a part of how mechanics, or in general any good situation, is solved. So you cannot claim that the other guy or the other person had a better luck guessing, okay, because the good thing about guess and luck is that it always fluctuates with time. So one time someone may be lucky, the other time someone else may be lucky, and so on. So that's how you have to work around this. Okay, now if you have multiple contacts, okay, that means clearly more than 2. So count all of those friction forces and unknowns clearly, okay. So in this case, count the number of unknowns including all the friction forces as unknowns. Okay, now the number of so we don't really know at which of these out of say 10 contact points, which of these contact points have impending slip and which one of them have no slip, right? That's the whole sort of idea to go about. Now the number of contacts at which there is impending slip equals the difference of the number of these unknowns. And the number of independent equilibrium equations. Of all bodies. So that's how you can do the counting. Again, the assumption part has to come. Assume specific locations of these contacts. So it will just be a number which you will know that the contact is happening, sorry, impending slip is happening at these many contacts out of the given number of contacts points, okay. So this part will tell you that. Then you have to do the assumption of impending slip at these locations. Assume specific locations of these contact with impending slip, okay. And for these contacts you can just write this, okay. Again this for say contact point 2 it will be F2 equal to mu S2 N2. For contact point 7 it would be F7 equal to mu S7 to Ni N7, okay. Again here this is not index notation. I think it should be clearly told. It cannot be, for example, okay, because I mean if you have Fi on one side there has to be at least one I on the other side, but just to specify this is not index, so you should not repeat it. So don't write it as mu S1 N1 plus mu S2 N2 plus mu S3 N3 and so on, okay. So that's something which you should note. Now again solve the equations of equilibrium, okay, and then check whether say Fj is smaller than mu Sj Nj where at other places, meaning other than this, okay. So meaning the other places would be no slip, right. So this check has to be made, and if all of them are correct, then what you have assumed is correct, and if not, then you were wrong, and then you have to keep on working. So this will clearly require more number of iterations. Okay, so that's how one can approach a problem like this. Okay, so these are normally linear problems for us to solve, but it's quite fun to solve it and eventually find the correct answer. Okay, uh, again a small discussion is about, say, friction grips and friction locking. So the idea is that if you have, first of all, you should know what a friction grip and friction locking is. For this you have to use some sort of an internet search browser where you can see some videos and animation. So know what this is. Okay, so you should proceed ahead only once you have figured out what is friction grips and friction locking. Okay, and it finds it's used in power screws and some other situations as well, but just understand it in the more general ways for now. Okay, so the friction grip is designed to loosen that is begin to slip a specified load. So if the load is until this value, then there is no slipping. If the load increases that value, the slipping must begin. So it is designed in a way, that's the important part. We know that at some value slipping eventually starts, but now we want to design a machine, okay, or an element of a machine such that this happens, and we set that value that the load slipping should start at this. Okay, the other case will be friction grip is designed to lock itself. Okay, this means that the slip cannot occur irrespective of loading magnitude. So this can be ensured that how is this done? I mean that the reaction is inclined to normal at an angle less than phi s. Okay, so reaction is inclined at an angle less than phi s is equal to tan inverse mu s. Okay, so see these situations and examples, and then you will understand the hype about friction is not underrated. Okay, it is very, very important in most of the things which work around us. Okay, let's take up a wedge as another special case. Now let's first define what a wedge is. Okay, you already know, perhaps you already have a picture of it, but let me define it formally for us. A wedge is a small block having two flat surfaces. With a small angle around 5 degrees between them. Okay, now just like the machines which we simple machines which we have referred, it has a purpose, and remember what was the purpose? That it transforms an applied force into a much larger force approximately at right angles to it. That's where the small angle is relevant, because the transformation is approximately right angles to it. So this can be used, to say raise heavy loads and so on. So let me just show that first. So you have, sorry, this is alpha. This angle is clearly alpha by 2. This angle is alpha by 2. Okay. So this is a smooth wedge. And if you want to write the equilibrium angle equations, remember the angle alpha is small, okay? So the sines and the cosines will really be simple in this case. So fx in this case, we know the x-axis and y-axis. So fx would be equal to p minus n1 plus n2 sine alpha by 2. This is equal to 0. Okay. Fy is equal to n2 minus n1 cos alpha by 2 is equal to 0. So when both of them are taken together, then you can say that n1 is equal to n2 is equal to p by 2 sine alpha, which alpha by 2, which is equal to p by alpha. Okay, sorry, this is p divided by 2 sine alpha by 2. Okay. So since this angle is alpha is small, so sine alpha by 2 will be equal to almost equal to alpha by 2, and when that is multiplied by 2, that becomes alpha. Okay. So what this implies is that for alpha is equal to 0.1 radians, 5.7 degree. Okay, n1 will be equal to 10p. That, what does that mean? That if you apply a small p, okay, then it gets magnified to n1. Okay, and that's the idea of, say, if you have a wooden log over here, This is a wooden log, and this is an axe handle, and this is an axe blade. So we with our hands can only apply a small force P, and then N would become very large, and the crack which you have, this is the crack, this gets enlarged. Okay. Now this was a smooth wedge clearly. Now let's take a sort of a rough one where friction is present. So let me draw that. N2, and then say this angle is alpha by 2. This is also alpha by 2. And then you have F1, you have F2. Okay, so this is rough wedge, rough or non-smooth wedge. In this case, we will again sort of let's see the unknowns in this one. That is what N1, F1, N2, F2. Okay, equilibrium equations, Fx equal to 0, Fy equal to 0. So 2 unknowns are 4. So this becomes a statically indeterminate problem. I mean, you should also think about the moment balance at both of these examples. I'm putting a question mark, okay, in both this smooth and the rough one. Okay, once that is done, okay, so now if we want to see this as a problem, not to actually find these values, but to check it as a problem of impending slip. Okay, this is statically determinate. So let's see. So problem of impending slip, and we want to sort of impending slip to the right. So let me draw that again. N1, N2, okay, so sorry, it should not be mu and 1. Okay, fine. So let's see. Fy is equal to 0. This would imply N1 is equal to N2. This is equal to 0 by symmetry. Okay, I mean, we don't want the wedge to be accelerating in the y direction. So fx is equal to 0. For this we would have p is equal to n1 plus n2 sine alpha by 2 plus mu n1 plus n2 cos alpha by 2. And because it is impending slip, so clearly f1 would be equal to mu n1 and f2 would be equal to mu n2. So n1 is equal to n2 is equal to 0.5 p by sine alpha by 2 plus mu cos alpha by 2. Okay, so that's how we are saying that the problem of impending slip, it's a statically determinate problem. So if you want to say right, the force in the y direction, the force F in y direction on a face of a wedge F is equal to n2 cos alpha by 2 minus mu n2 sin alpha by 1 minus mu tan alpha by 2 tan alpha by 2 plus mu. So one of the things which you should note that we are not actually making this assumption of alpha being really small until we need it at the end. Okay, so 0.5 p cot alpha by 2 plus phi. Phi, as you know, is tan inverse mu, friction angle. So if you see the ratio of F by P, okay, that is equal to what? 0.5 cot, sorry, cot alpha by 2 plus phi. So for alpha is equal to 5.7 degrees, F by P will be equal to 10. For mu is equal to 0, F by P will be equal to 3.32. For mu is equal to 0.1, F by P will be equal to 1.98. I mean, you can use a calculator and do this. Okay, for mu equal to 0.2, F by P would be equal to 1.41. For mu is equal to 0.3, F by P would be equal to 1.09. For mu is equal to 0.4, F by P is equal to 0.89. For mu is equal to 0.5. Now clearly F by P decreases with mu, so F by P is decreasing as mu is increasing. But what you should notice over here, that it is very sensitive to the small change in mu. So just by changing the mu by 0.1, you reduce this ratio f by p, say from 3.32 to 1.98, and from increasing it from 0 to 0.1, which is a frictionless surface, to 0.1, that f by p ratio reduces to by almost 1/3. So this is something which is important for you to know, that it's highly sensitive. This expression is highly sensitive there. Okay. Now similarly, if there is a, let's see, let me draw the diagram first. If you have into alpha by 2, alpha by 2. Okay. Now if you have a, for a given wedge, meaning alpha is fixed, you may P1 needed to keep it in place without being squeezed out. Okay. Without, sorry. Squeezed out. Okay. Now in this case, I mean, the direction of F gets reversed, and that is shown in this figure. Okay. So what we have is this situation. You can see that there is a this outward mu n1 which is going in. Okay. And that is squeezing out. But now the objective of this P1, this inward P1 is that it should keep it in place without being squeezed out. So in this, the direction of F gets reversed. Okay, direction of F, and F, if you recall, is this force F in y direction on a face of the wedge. F gets reversed, and in this case the friction will act in the opposite side. So minus this mu in this expression can be replaced by minus mu. So one would have F by P1 is equal to 0.5 into cot alpha by 2 minus phi. So the wedge is self-locking if P1 is smaller than or equal to 0. That means, I mean, it will not be squeezed out. Okay, because you do not require any P1, positive P1. Or this means that if alpha by 2 is smaller than equal to phi, okay, or tan of alpha by 2 is smaller than equal to mu, because tan of phi is mu. Okay, now the last claim which we are making over here is that it is beneficial to have a certain minimum value minimum value of mu, so that the wedge is self-locking. Okay, let me just draw a diagram. So you have, say, this is N, okay, this is F, and this is the resultant R. This angle is again alpha by 2, okay, and then you have an R again on this side. So without P1, I mean that's the condition for self-rocking, right? I mean P1 is smaller than or equal to 0. Without P1, the wedge is in equilibrium under two forces, which must be equal and opposite. Okay, as is shown in this diagram. For self-locking, F by N is equal to tan alpha by 2. Okay, this is just this triangle. Tangent of alpha by 2 is equal to F by N, and this is smaller than equal to mu coming from over here. Okay, so that ends our discussion about at least some of the special cases of friction. So before we learn about the flexible cables on rough surfaces, I request you to please look up how flexible cables on rough surfaces are used in moorings and belt drives and band brakes in hoisting rigs and belt convergers. So you should be belt conveyors, sorry, okay. So you should be looking at either pictures or videos from the internet to exactly understand what these are and how they involve flexible cables on a rough surfaces. You should move ahead only after seeing this. So please pause the video right now. Okay, now since you have seen all of these applications, you must notice that the condition in all of them, that the condition of their impending slip is an important criterion for their design. Okay, so please check back all these applications again if you could not agree to this statement that the condition for impending slip is very important in the design or how they work. Okay, so if you recall, we have already learned about some of the basic results of a belt moving over a surface. Okay, we had derived a ratio between T1 and T2 and so on. Okay, so revise that part, let me put that. Belt moving over surface. So this has been done earlier in this course. Please go back and check and see all those results. So if you have, say, V is equal to 0, then the relation P is equal to T by rho for normal reaction P per unit length. Okay, implies P is proportional to T and P is inversely proportional to 1 by rho. Okay. So clearly if the tension is larger, P would be larger. If rho is small, then P would be large. Okay. So if you have, say, a box like this, say this is a package, and I want you to focus on this particular part. Okay. So in one case I'm drawing like this, in the other case, say it's something like this. Okay. So you have a so-called sharper edge, and this is a somewhat of a blunter edge comparatively. Okay, you can always make this angle theta or the curvature, whichever way you want to see the sharpness or the bluntness. So you know that if you have a, say, a parcel tied, so package, parcel, box, whatever you want to call it, a parcel tied by a string around it. Okay, so this is the string which, okay, this is the string, this is the string. So parcel tied by a string around it, the sharper the edge of the parcel, the smaller is rho. And greater is tendency of the string to bite into the parcel due to larger P. Okay, the sharper the edge of the parcel, the smaller is rho. Okay, and with this curvature being smaller, the greater is the tendency of the string to bite, because if rho is small, then P will be large, and hence there is a greater chance it will bite into the parcel. Okay, now T and P vary exponentially with theta. So if you recall equation 2.76, please pause the video, go back and check equation 2.76. There you have T1 by T2 is equal to e raised to the power of mu s theta. Okay, this is for impending slip. Okay, now this implies T1 by T2 is independent of size shape of the curve. Okay, T1 by T2 is independent of the size and shape of the curve because of this equation which we had derived earlier. So all it depends is clearly this mu s, which is the friction coefficient between the belt and say on whichever surface it is acting, and this angle theta, which essentially is the change in the direction of the belt. Okay, so sorry, let me just show that. So for example, theta is the change in direction of belt. For example, if you have say something like this and you have something like this, then the theta in this case would be pi, this would be pi by 2. Okay, so that plays a role over here, and the friction coefficient, it is quite clear. This is between the rope or the cable and the surface over which it is there. Okay, now so T1 over here, when using this, you can write out as T2 into E into mu s theta, and this exponential increase in this tension T1 is of great practical utility. How is it? For example, if you take theta is equal to 2 pi, okay, and this is irrespective of the shape. You have to measure theta as the change in direction of the belt. Okay, don't get confused about the shape. Many a times, due to design reasons, the shape may or may not exactly be like the one which you see on your screen. Okay, anyways, so theta is equal to 2 pi, for example, in one case. Now if mu s is small, even then, if you have say multiple turns, then e to the power of mu s theta will be large. I mean, it's called an exponential function because it has this sort of an exponential behavior, so it rises very rapidly up, and with more number of turns, like 2 turns, 4 turns and 5 turns, you can just it will be a lot of value. Okay, so let's take up an example of this. So if you have say mu s is equal to 0.25 and there are 4 turns. Okay, so in this case T2 by T1 is equal to e to the power of mu s into 8 pi, 4 into 2 pi, and this value is what, 0.0019. Okay, so this is how small the tension ratios are, or large, depending on how you see T2 by T1 or T1 by T2. So see that in words, a load of T1 is equal to 20 kilonewtons, okay, can be held by applying a very small force of merely 38 newtons. This is 20 kilonewtons and you have 38 newtons. Okay, and as you say, take 8 number of turns, not 4, then the value of T1 in that case can be what, 109.00 kilonewtons. Okay, for 8 turns, T1 will be equal to this for the same T2, 38 newtons. So that's the important part about this, that it can be used for, I mean, you can hold a ship by this idea, and you must have seen this in when you had learned about these things. Okay, so that's the practical application, engineering application of this idea. Okay. Okay, so you must have learnt about moorings. Okay, I mean the sufficient number of turns will cause this. So gradually, I mean, as you can see, if you take up more number of turns, how how much more tension you can hold on the other edge. Okay, and the concept is that if you have more number of turns, you can take a T2 which is very small. I mean, just let it be on the ground. Okay, it's that small, and then you can have this T1 is very large. So please look up pictures of this and you will realize this. Okay, the slack end may be even left on the ground. That's how important this exponential relationship is. Perhaps it's not easier to identify it when we had learnt it in equation 2.76, but now you are sort of matured enough to appreciate this slightly more. And why will it be, I mean, if it's enough to keep it on the ground, there is a friction, okay, from ground. That will provide it enough T2 so that a very large T1 can be held. Okay, same idea is used for hoists. Okay, now you can also explore the same relation, which I will write over here in red so that you can investigate it. The relation T1 by T2 smaller than e to the power of mu s theta for no slip is fundamental to the mechanics of cloth and strength of knots. Okay, so please investigate how strengths of knots can be used using this equation T1 by T2. Okay, the no slip condition. Okay, so up next we can take up this topic on rough pin joints or journal bearings. So let's try to understand what it is. So if you take up a shaft or axle, you should by this stage know the application of each one of them, or pin of radius r at rest in a short cylindrical cavity called a journal bearing. And this has the same radius as well, same radius. So let me show how it looks. This is, say, O. This is the radius of this pin or shaft as r. Say this is I hat, this is j hat, and say this is the force P acting on it. Then let me show this. So the cavity is shown by this. Say you have this R as the resultant force. Okay. So if you have a clearance, so most of the moving machine parts have a clearance just to allow some space in case of an expansion. Okay. So inevitable clearance results in a line contact. When the line contact is between the pin and the cavity called the bearing. Okay. So say this is the rotating part and this is the stationary part. Okay, so then we will have a line contact over here. So this is what we are referring to. This is a slightly modified figure, but yeah. Okay, now you have this force, transverse force pi hat. Sorry, I should show this p in direction I. Okay, you have p. Okay, pi hat acts on the axle normal to its axis z for equilibrium. Then the bearing reaction R will act in on line of contact opposite to P. Okay, so R will be equal to P. So this is where the contact happens in this particular way. So this inside the screen or outside the screen will be the line of contact. Okay. Now because it's a pin or a shaft or an axle, it will clearly be deriving its power from somewhere, because perhaps it has to move a car ahead and so on. Okay, so let's show that. Okay, sorry, let's show that. So I'm just seeing this shaft or the axle or the pin. So let me call this point O, Y, X. Okay, and then this P is acting in this direction, and this reaction N, and then you have this mu S N, and then I'm showing this M. Okay, this is the force which is, say, coming from the engine, okay, on the shaft, the axle. Okay, so you have a external moment M applied to this axle, about its axis to cause impending slip. Now the line of contact, and let me put that in red so that you can also sort of grapple with this idea. The line of contact cannot be opposite to P since f in the y direction is 0 is violated. Okay, the line of contact cannot be opposite to P, since this earlier thing was assuming that this R will act in the direction of P on the line of contact, but over here if you sort of break this R into n and mu s n, you will realize that if the line of contact is taken opposite to P, then this particular thing will be sort of unbalanced, and hence force in the y direction will not be equal to 0, and that would mean it would start accelerating in the y direction, something which we don't want. Okay, so then we want this axle to be in equilibrium under this applied force P, the applied couple M, okay, and the reaction R of the bearing. So that would mean that equilibrium axle, you have F is equal to R plus Pi hat has to be equal to 0. This implies R is equal to minus Pi hat. Okay, so is in direction opposite to Pi. Okay, we have not really now taken the balance of this mk has not been balanced. Okay, now this should be positioned, so it cannot really be opposite. Okay, that's what something which we have established. So let me now draw another one. Okay, so the direction is opposite, but it's not along the same line. So let me show that to you graphically. Okay, say this is P. Okay, and then this is R. Okay, so R is equal to minus P, so the sense of the direction is clearly opposite, no problem. Now this is what? Y, this is X, this is A, phi, D, okay, and this M is acting as it is in the so-called K direction. Okay, now this R is made up of two components. One will be the normal, see this angle is phi, this point is B, and the other is clearly friction, mu s n. Okay, and this is the so-called friction circle, which is RF. The RF of this is R sine phi. Okay, now let's try to see this. So F is equal to R plus Pi is equal to 0, so that means R is in a direction opposite to Pi. Now it should meaning R should be so positioned on the axle that it causes a moment about the axis opposite to MK. So that the equation MO is equal to 0 is satisfied. Okay, and this is required because the axle or the shaft does not have any angular acceleration. Okay, so that's why the equilibrium is necessary over here, just like the equilibrium in the x and the y direction was necessary. Okay, so with this figure you can write that n is equal to r cos phi. You can write, mu Sn is equal to r sin phi, and clearly this automatically implies that mu s is equal to tan phi. Okay, no guesses there. So r is clearly at an angle of phi to n, you can see that over here, and phi is equal to tan inverse mu s. It's the so-called angle of friction. Now MOZ, okay, along this k direction, x cross y, so coming out of the screen is m minus mu s n r is equal to 0. So n does not contribute to the moment because it's along the line. This implies that m is equal to mu s n r, which is equal to, so mu Sn can be taken from over here as r sin phi. So this is written as r into r sin phi. Okay, and this becomes equal to p sin phi, since the magnitude is the p into r sin phi, sorry. So we are only taking the magnitudes over here. Okay, so with that we can write 4.11. So this implies that for impending motion, r does not act radially, but at distance of Rf equal to r sin phi from axis. Okay, you can see that over here r is not acting at along the axis. It is acting at a distance of Rf. This is Rf, this distance. This is equal to r sin phi. Okay, so that's where this is acting. So this circle is called the friction circle of the axle. I think we had already shown that over here. Okay, yes. This circle, and let me show that in another color. This circle is called the friction circle for the axle and the bearing. Okay, so it's not just for one of them, we call it for both axle and the bearing. The whole combination has to bear and is independent of loading conditions on the axle. So it's not really dependent on P, okay, which is the loading on the axle. Since RF depends on R sine, RF is equal to R sine phi. R is the radius of the axle, so it's independent of the loading, and phi, as you see, is the friction angle, depending only on the friction coefficient. So that's why it is written that it is independent of the loading conditions on the axle. Okay. Now you can clearly see from this that the contact occurs at B. I mean, that's why we are showing the friction, etc. over there, and it is some distance away from A. A is this distance which we had earlier intuitively thought would be. So contact occurs at B, riding some distance away from A, okay, and this is one which is opposite to P, but it doesn't really act over here in a direction opposite to M. Okay. So physically, when the applied moment M is gradually increased on the axle rolls without slip on the bearing, so that climbing on the direction opposite to M takes place until slip occurs. For a rotating shaft, mu k's will be equal to tan phi k, and the radius of the friction circle will be r sine phi k. Okay. So let me put that in words. And this is how any motor or machine or engine starts. Okay, so this is how that so-called first earlier transient state happens. The noise which you hear, okay, some of it may also be coming because of these things. Okay, so when the applied moment M is gradually increased on the axle, the axle rolls without slip. On the bearing, so as to climb in direction opposite to M until slip occurs. So you should be able to understand and visualize this text written in red based on what we have just discussed. Okay, now once the shaft is rotating, so called rotating shaft, mu k is equal to tan phi k. So mu k is the kinetic coefficient of friction, then the radius of friction is what, r sine phi k. This will be equal to r sine phi. Okay, this was for the impending slip and this is for the rotating shaft when it actually comes in the steady state. Okay, and this will be there because mu k is less than mu s, and as you know that phi is actually equal to tan inverse of mu k is mu s, sorry, tan inverse of mu s, and this is phi k and this is phi s, and hence sine of phi k be smaller than sine of phi s. So that's where this is coming from. Okay, now let me take up another case that if you have say a line of contact at E, let me just take up one. Okay, so let's take up this as RF. This is the R. RF, as you know, is the friction circle or the radius of friction. Okay. Okay, and then okay, theta, and this is phi. Sorry. And again this angle will also be phi. Sorry. Oops. Yeah, so this particular angle will also be phi. So this is what we are calling as angle theta, and phi is on both the sides equidistant because RF is the same, and this is the contact point E. Now over here, let's take this as R, N, R2, H, and then this is R1. F, this is what N. Okay, fine. Let's now understand this. If you have a line of contact at E, okay, E is shown for no slip, R makes an angle theta, perhaps I can show that with this. Okay, so this is R, actually only until here, but I've shown this blue line just to show that line of action. So R makes an angle theta which is smaller than or equal to phi, okay, with the normal, so normal or the radial line. So theta is with the normal radial line. Okay, so this also implies that the line of action of R, the blue line which you see, R lies between, I think it's a vector, so I should show it with a vector. Okay. The line of action of R lies between tangents to the friction circle.
from contact E with R1 and R2 as reactions for impending slip. So R1 is actually along this tangent. This is R1. So okay, so you can see that this lies between the tangents to the friction circle. So these are the two tangents to the friction circle from E. Okay, and they have these respective reactions for impending slip as R1. So if this was the green line was actually for the impending slip, then you would have a reaction force R1 in this direction, just like which we have done. So it would be off by an angle by a distance RF, and similarly over here you would have an R2 by a distance RF on this side. So the reality in this particular case is that the R would be lying at an angle theta, which is between these two tangents. Okay. Now the equivalent reaction at the axis of the axle is a force, say R, and frictional moment that will be equal to R into mu s n equal to R into R sine phi. We have seen this before about pin axis. Okay, in a direction which is opposite. Impending rotation. So the effect of pin, the effect of friction, can be decreased by using pins of small radius r. Okay, so you should learn about the Jewel watches and how this idea is applied over there. This is something which you should do. So small values of mu s, you can say that mf is equal to r sine phi, since this can be written as tan phi or r mu s. So sine phi and tan phi are same if the angle phi is small. You should be aware of a sinusoidal and tangential series also. So just take the first term, you should be good to go. Okay, and this is phi r tan phi mu s into r. So if you have a smooth case, mu s will be equal to 0, and what would this imply? That the friction radius of friction is 0, which implies that the reaction R passes through the center. So it will not be off by a distance RF. Now if you have a rough case or a so-called perfectly rough case, so mu s is infinite. This implies that phi will be equal to pi by 2. You can take a limiting case as well. Take mu s as tending to infinity, and in that case phi will be tending to pi by 2, using just this one. Okay, and that would also mean that RF in this case would be equal to R. This implies that the friction radius will be equal to the radius of the axle. Okay, so RF will be almost be equal to R. Okay, now coming back to this one. So if there is a contact at E, then the reaction R, so this case which we are discussing now is this case. Sorry, I should put another ink. Perhaps red only is the remaining one. Okay, so this RF equal to R. So see diagram. Now in this case, if RF is equal to R, then the reaction R which would be acting has arbitrary direction below the tangent line GEH. So if you see this tangent line GEH, okay, and it has these limiting directions HE and GE, HE and GE. Okay, so then the R will be below the tangent line GEH. Okay, just because RF in this case will be equal to R. So it's a limiting case, and in this case clearly slip cannot occur because you require something for slip to happen, and that condition cannot be met. So let me put that slip cannot happen, and you should find out why. I think it's already contained in these, but you should do that. And finally, for the sake of name, I should mention about sort of rolling friction, which you will learn using the solved examples in your text. Actually, even for the journal bearing, you have to learn the solved example with this, how to solve a statics problem in mechanics for rolling friction. So you should just see the solved example, because there is no new theory to be learned at this stage. Okay, so that's where you can perhaps close these discussions related to friction before we move on to the bars and trusses and beams. That would be the last topic of our discussion in statics.